Can everyone hear me? Can everyone hear me? Okay, yeah. Okay, welcome back. And then the first thing is that there's no office hour tomorrow because I need to attend 2 conferences tomorrow and then actually host 1 section. And that section is right around the office hour time, 2 hours. So I have to prepare for that. And then the second thing is kind of interesting is that nowadays the conference are online, and then it's almost like having an online class. And then when the host asks a question, usually it's completely silent, even though the Zoom meeting has like more than 100 people. And then, and then the host has to say that, okay, can someone give a response because I've been speaking for 2 hours? And it's kind of feel like, I'm on the other end of the screen. And but to be honest, it's kind of fun. Like, if the talk is not interesting, I can do my own stuff on my computer. So I don't know if that's the same feeling to you guys. Okay, we have 10 people here. Okay, we can get started. I guess if I reduce my recording quality, there might be more real-time participant. Okay, so. Let's first briefly review what we have taught last week. All right, so last week we looked at a few experimental examples that people use to develop quantum mechanics, and then we came up with 3 postulates. And then the first postulate is you have to use a wave to describe a system. And this one, I think I've probably said it too many times, and then you should already remember this very well. And then the second postulate is that this the way to understand this wave function is that the amplitude square of this wave function gives you the probability density. Probability density of the electron showing up at position x and time t. Okay, that's the second postulate. And then the third postulate is that if you have 2 possible configurations of the system described by wave function psi 1 and wave function psi 2, then their linear combination is also a possible wave function as long as it's properly normalized. Right? You need to normalize it because the overall probability of finding an electron in the entire space is 1. Okay, so this is what we learned in last week, and then we actually gave 2 examples. One is the fact that one is to use wave to describe a very classical case that the electron is at position x1, right? And then there we discovered that unfortunately the function is not well defined and it's actually explode, and you have to use a delta function. Okay, you have to use a delta function. And then the second thing we look at is that we look at the plane wave. Okay, we look at the plane wave, and then we found that what the plane wave means is that when you do the amplitude square, this is the real part of the wave function. Okay. So what we see is that for a plane wave, if you calculate its probability density, it shows that it's uniform distributed around the space. It's the probability of finding an electron here and there, they are all the same. So it's a normal, it's a plane distribution. And then we also showed that, okay, you can kind of see that the wavelength, because it's a delta function, there's really no periodicity here. So the uncertainty for the wavelength is infinite, and thus the uncertainty for the momentum is infinite. Here you can see, because you can find the electron everywhere with the same probability, so that the uncertainty of the position of this wave is also infinite. Okay. Now, at the end of last class, we also say that, okay, if you use this one as EIK1x, this is EIK2x, right? Two plane wave, when you add them together, then you will create an interference pattern. And then you will see that originally, although you can find electron everywhere, okay, with the same probability, both of these waves have a flat distribution of the probability, but then when you add them together, you can find spots that actually have zero probability of finding electron, and that's interference, which is very common for waves. Now, before we go any further, I want to introduce the concept of Fourier transform. Okay, the Fourier transform is probably something you guys have already learned in one of the mathematics class. And if you haven't, then you can also go to Wikipedia. You just go on YouTube. There are actually numerous great videos, to be honest, great videos of Fourier transform, which can probably explain better than I do. The reason that I want to introduce Fourier transform here is that if you take a look here, there's already a pattern here. Is that there's a connection between position and momentum in quantum mechanics. Okay, just like there's a connection between time and frequency in any signal analysis. Right? If you have a time varying signal, voltage signal, then you can apply Fourier transform and you can see its frequency spectrum. So here's the same thing. For example, this one, the uncertainty of position is 0, uncertainty of momentum goes to infinite. This one is uncertainty of position goes to infinite, uncertainty of momentum is 0. Okay. So there's actually a deep connection between position and momentum, and there are two different ways you can kind of look at this. The first is a wave in the form of wave, and this one we'll actually dig a lot in details. And then the second way is actually using operator. We'll also talk about that. That's the Heisenberg's approach. Now, let me first say about the just write down the Fourier transform in terms of mathematics description. Okay, the Fourier transform, what it says is that any smooth, if I give you a smooth function fx, okay, you can write it down as an integration of another function, okay, times eikx dk. Okay, so this is the mathematical expression of Fourier transform, and you can kind of, well, there are many different ways to understand this, but in quantum mechanics, the way we can interpret this equation, first of all, it's just a mathematical expression. You don't have to interpret it you don't have to add a physics meaning to it, but we can, if that helps with us to understand quantum mechanics. If you look at this, is that the integration is like sum, right? Integration is similar to summing up different functions, different terms. And then this term here, if you look at it, this term is just a plane wave. Right? This term is just a plane wave. And what is this? This is the coefficient in front. You can kind of think of it as a weight, but it's not really a weight because it can be positive and negative. It can even be a complex number. So you can you can imagine it's a weight, but it's not a real weight. Okay, and then so what it really says in the Fourier transform is that for any wave function in quantum mechanics language, any wave function can be expressed as the superposition, right, as a sum, the superposition between a lot of plane waves, right? Each plane wave will have a coefficient in the front, which you can understand it, kind of understand it as a weight, but it's not a weight. Okay, so this is so this is really saying that all the function can be decomposed into superposition of plane wave. Whatever wave you have, decomposed into plane wave, and then you can have a good approximation of the wave. And I remember, like in the real mathematics history, that when Fourier first introduced Fourier transform, it's actually a little bit of debate over whether it's really correct or not, because you see anytime you see infinity, it's actually introduced some debate. But really the thought here would be, okay, the Fourier transform, if you think about it, of this function can be expressed with another function. What it really says is that you have infinite amount of variables k that you can use it to approximate to this function, right? So it's like, in terms of machine learning language, maybe this is more popular now, you have infinite amount of parameters you can tune in your model. Okay, so those parameters are the fk. Okay, and of course Fourier transform would have an inverse, right? Mathematically, you can convert a function to its Fourier transform. You can also convert it back. So we're not going to explain this. This is just mathematically, it kind of, you can prove this. Okay. Okay. So also in quantum mechanics, often we write it down as, because wave function we write down as per psi, right? So we write down as per psi, and then this is per psi tilde k e minus plus. Okay. Okay, so in quantum mechanics, write it down in this way. Now, my question is, how do we interpret per psi here? Does it have any physical meaning?
Can you explain the difference between the left and right equations?
These two?
Yes.
Okay, so this one is the inverse Fourier transform, which means you already know fx and then you want to convert it to fk. Right? It's, in terms of measurement, you can think of it like if you start with an oscilloscope, then you're measuring a function, a voltage in terms of time, and then you can do Fourier transform to convert it into frequency. But then if you start from a spectrum analyzer, then you first measure the frequency, and then if you want to know the time, you have to do inverse Fourier transform to get the time domain. So these are just just for completion. Okay, there's this. So the question is that, okay, in Fourier transform, for example, in signal analysis, there's actually a meaning, right, for your Fourier transform. When you acquire a voltage signal on oscilloscope and then you do Fourier transform, what you have is a power density spectrum of your signal, right? And then that thing can actually be measured with electrospectral analyzer, and then you can actually compare these two. They are the same. How about here? So we have the wave function in position. Its amplitude square, meaning the probability density of finding the electron at position x. Right. So now if you do a Fourier transform, you transfer the function into a function of k, which is a function of momentum, right? Because h bar k is the momentum. Does this wave function has any physical meaning? Can anyone make a guess? Can anyone make a guess? Oh, let me put it in a different way. Let's say here, in postulate 3, suppose I have a superposition of wave function, and let's forget about normalization. Okay, so if I want to measure momentum of this equation, of this wave function, what it really looks like is that you have half of the probability that your wave function look like this, and then you have half of the probability your wave function look like this, right? Because they're equally weighted. So if happens that the measurement result measures this one, we'll later explain this a little bit more. If it happens that the measurement result shows this half, right, because its probability is possible, then you will measure a momentum of h bar k1. If you measure this half, if the probability gives you this half, then you measure h bar k2, right? So the coefficient in the front actually represents the probability of measuring the momentum. Okay, so if you do this in the language of postulate 2, what it really tells you is that this wave function, when you do amplitude square, gives you the probability density of measuring h bar k. Okay, and if you don't understand it, that's fine, because we'll introduce postulate 4 to 6, which you will see actually more clear the meaning of this. Okay, so now
It's just a probability density of the momentum.
The amplitude square of this is the probability density of the momentum. Yes.
Okay.
Yeah, it's the same as this function is the probability density of the position. Okay. We'll talk a lot more about this later. Okay. So now let's try to apply this Fourier transform to try to see, okay, the connection of momentum and position in these two very simple examples, right? You have a particle in a certain place, and then you have particle everywhere. Okay, so now let's look at this. Okay, let's make it very simple because there's actually a normalization problem, and let's ignore that. Let's say for this wave, okay, your wave function is a delta function at position x equals x1. Right, at x equals x1, the wave function explodes, then of course its amplitude square also explodes. And you say, okay, but it's not normalized. Yes, it's not normalized, but just for simplicity, we write it down like this. Okay, and then if you do Fourier transform of this, okay, if you do Fourier transform of this, let's see, you already know per psi x, and then if you want to know per psi tilde k, right, you want to know the momentum space, then you can do this inverse Fourier transform, right, which is just an inverse of the Fourier transform itself. So this gives you a delta function e to the minus I kx dx. All right, just do this integration, And if you guys know about delta function, it's actually quite simple. Anything with the delta function, the integration give you is, let's put it, where can we put it? Let's put it here. Fx delta x minus x1 dx give you, let's write down here, give you fx1. Okay, just give you a function at position x1. And the reason of this is that you can think about this is that when x is not equal to x1, it's 0, right? So the integration of all those parts are 0. So the integration only has non-zero components around x1, right? You can say x1 minus eta, x1 plus eta, right? It's equivalent to minus infinity plus infinity. And then fx delta x minus x1 dx. Okay, so at the limit of eta goes to 0, if your function is very smooth, what it means is that you're integrating in an infinitely small interval, right? In this infinitely small interval, then your function f is not changing a lot. It's a very smooth function. That's the requirement. If a function at x equal x1 is like changing from 0 to infinity, then this doesn't apply. But for a smooth function, in this small areas, you can always have, let's say, fx plus epsilon goes to fx, right? It's a very small area, and then you approach it. And if that's the case, then this is just a constant, because no matter how you move, the function is always at value fx1, right? No matter how you move, because it's very small, so that it's a constant that we can move it in the front, f1, and then the remaining here is limit epsilon goes to infinity, goes to 0, and then you have integration, and then it's a delta function, right? And then we already know the integration of delta function. If you include x1, okay, in this interval, then the delta function integration is 1, right? That's how we define delta function, is 1. So this part is 1. So overall, this is fx1. Okay. Another way to think about this is that your delta function is 0 everywhere, but infinity at this spot, right? So your delta function is like a sampling point, right? Where it points, it actually measures that point. Okay. If you think about the multiply a delta function with another function, it's like you're trying to sampling the intensity of the other function. Okay. So if you use this delta function, okay, apply it back to the Fourier transform, then what you get is that, okay, this is a function fx, and so it's e to the minus I k x1, right? It's e to the minus I k x1. Oh, there's 2 pi here. Okay. Okay, and what you can see here is that the amplitude square of this function, which will represent the weight, of your plane wave, right? The plane wave with momentum k. You will see that this always equal to 1 over 2 pi. Right? It's not normalized, so there's a normalization factor there, but we'll kind of throw it away. So what it tells you is that if you look at it in a momentum regime, it's actually a plane wave in momentum region. It's like you can find the momentum everywhere, and then they have the same probability, right? You can say the momentum of 0 has the same probability of momentum at infinite, right? They have the same probability. So that's why, okay, that's why if you calculate the delta p, okay, just use the definition of variance, and then you can see that this goes to infinite because your wave function has infinite, your momentum, your probability of the momentum at infinite is actually the same as your momentum at 0. Okay, so this is kind of explain, okay, why intuitively we say that because this doesn't have period, right? It doesn't have a wavelength. The wavelength uncertainty is infinite, so thus the momentum uncertainty is infinite. Now with Fourier transform, we can actually show it in a mathematical way that your uncertainty of momentum has to go to infinite when you are sitting at a position. Okay, and this is a very interesting question now. Is there a consequence of momentum uncertainty going to infinite? Does that create anything unphysical? Can your momentum actually go to infinite? What does it mean if your momentum is infinite? Let's say it's a free electron, so its energy is momentum squared divided by 2m, right? Fine with this? Okay, this is the energy. So if your momentum uncertainty goes to infinity, also meaning that your momentum has the probability of going off, also mean that you have certain probability of finding a momentum at infinite. What does that mean for your energy?
It's also infinite.
Yeah, so there's uncertainty of the energy is infinite, and then you also have probability of finding your energy at infinite, right? So actually, people will tell you that there's no need to normalize this wave function anymore because this wave function is unphysical. Because if you're really a delta function, what it means is that you would take infinite amount of energy to create that. Okay, so I know this is a little bit counterintuitive, that you say, okay, but what about when I see that a double slit experiment of the electron, there's indeed a dot, right? There's a dot there, and that's a position. But if you zoom in, the dot has a size, right? The dot is not infinitely a small dot, right? So also think about this if you still find it counterintuitive, the way to think about this is that how do we really measure something at a certain position, right? If you say that, okay, I can use a ruler, okay, but what about the position is smaller than your ruler? You say, okay, then I use a smaller ruler, right? Now, is there a limit of how small you can make that ruler, right? If you use electron, then okay, the smallest unit would be the size of your electron, right? If you keep going, then you're really not going anywhere unless you dig into the nuclear, right? So you can see that the idea of that you can know the position infinitely well, okay, in really a delta function infinitely well, actually contradict a lot of things, right? Just it looks like intuitively it's correct, but it's not, right? You feel it's right, it's just because in high school, in middle school, people taught it over and over again, and then you think it's correct, okay? And if we start teaching quantum mechanics before Newton mechanics, then you would think this is intuitive, and then Newton mechanics is not. Okay. Now a very quick look at the second example, right? Is that is this plane wave, right? Plane wave, and previously we say, okay, look, it has only one k, right? Let's give you a number, k1. It has only one k1, so that the momentum here must be h bar k1, and then that's it. That's what we say. Okay, and then you can also do this with the Fourier transform, and then to really test, okay, does this Fourier transform make sense or agree with that picture or not? So what you can do is that you can again apply this Fourier transform for the plane wave. Okay, and then you just write it down here. And then the integration is this, and your wave function is e I k1x, right? k1x, and then you have to times e to the minus I kx dx. Okay, and if you write it down a little bit better, it will look like this. You combine these two terms. Right, it's exponential I k1 minus kx time, and then do the integration. And if you look online, this integration actually, people will tell you this is ill-defined. Okay, think about this. If k1 not equal to k, then you will get, what you get is a periodic function, right? You get this is delta k, right? If delta k is not equal to 0, then this is a periodic function. And then if you, let's say if you integrate sine, give an example, minus infinity to plus infinity sine x dx, this is ill-defined. There's no value here, right? Because what do you mean by minus infinity? You can go half a cycle more, it's still minus infinity, and then your value will change, right? So it's an oscillation period, and then it doesn't really have a defined number. So in physics, like usually what people do is to say, okay, let it be 0. Okay, because overall it's 0, right? Because it's periodic up and down, up and down, up and down. Okay, and okay, so that's not important. Now let's look at the other part. If delta k is 0, okay, if k equals k1, then the upper part is 0, right? So it's exponential 0 is 1, right? So then you're integrating 1 from minus infinity to infinity, and what that means is that you get infinite. Right? If you're integrating 1 from minus infinity to infinity, you're getting x minus infinity, infinity, you're getting 2 infinity. Okay, this is a wrong way of writing it, but you can kind of get the idea. So this equation is kind of interesting. So it's that it goes to infinity when k equals k1, and then it's ill-defined when k is not equal to k1. And later in the homework, you guys will be asked to show that this is actually a delta function. Okay, this is actually a delta function. And so the meaning of this Fourier transform is very clear. If you try to measure the momentum, then the probability of seeing the momentum at k not equals k1 is 0. Right? Because it's delta function, k not equal to k1, then it's 0 everywhere. So all the probability of finding the momentum will be at k1, right? So this is exactly as what we interpret at the with this wave function. Okay. Now let's move on to the next 3 postulate, which is actually really, really interesting, and it's actually much more fun than the wave function itself. And let's see if we can get some of you, think really hard about this postulate. Okay. Now, if you look at postulate 1 to postulate 3, and you try to compare it with what you can do in experiment, do you see it as complete? Do you think the postulate is complete? We say that postulate 2 represent the probability of finding the electron XX, and then if you do Fourier transform, then you can get the probability density of finding the probability of h bar k is your momentum, right? So this 3 postulate combined with Schrodinger equation tells you how you can what you can expect if you want to measure position and if you want to measure momentum, right? If you want to measure position, this is your probability. If you want to measure momentum, this is your probability. But it doesn't tell you if you want to measure other things, right? What about I want to measure angular momentum? What about I want to measure spin? What about I want to measure energy? What about I want to measure wavelength, right? If it's a light or it's a, let's say also in electrical circuits, what if I want to measure the frequency? Right, so this 3 postulate, it doesn't tell you everything about what you can do in the experiment, so it's not complete. So the question really here is that now you say that the wave function completely describe the system, and then you give us Schrodinger equation which you can solve, which means that we should know everything about the system, not just position and momentum, but also spin, but also frequency, everything like this. So how do we get measurement result to read out those things, right? Let's say I want to measure the energy, right, which is a very fair expectation, right? You get something you want to know its energy. Now, so this is the question that the postulate 4 to 6 they try to answer. Okay, try to make the quantum mechanics system complete, theory complete. Now let's look at it in a classical way, how you would do it, right? So classically, okay, there's a particle moving, and then at its position at time t, right, when you fully solve this system. And then you can also say, okay, then because I know its position at time t, I can also know its momentum at time t. Okay, because there's a time and position one-to-one correlation, you can also say, okay, I know the momentum at position x. Right, this makes sense. It just tells you, for example, if you run to this spot, then if I'm observing you, then I can tell, okay, when you cross a line, your speed is this, right? You can see this in sprint all the time. So can we do that in quantum mechanics, right? If we think about this, then you might say, if I measure the momentum, or anything, not just momentum, but anything, okay? And I express momentum as a function of position, okay? And let's say I measure its expected value, right? Expected value, it's like the average value. Then you say, okay, at position x, I have momentum x. My momentum is at function x. And I know that from postulate 2 that the probability density of the electron being at position x is this, MT squared, right? Then you say, okay, this is a typical statistic problem now. If I know, okay, this is the value, I know the probability of it showing up, then if I do a sum, if I do a sum, then this will give me the average value, right? This is what statistical mechanics tells us, and then if you infer directly from classical mechanics. Does that look good? Anyone agree or disagree? So intuitively thinking, does this look good? Do you think it makes sense?
So the magnitude of the wave function gives us the probability of the position. But so how does that being multiplied by the momentum with respect to x give us the average momentum?
Because from statistical physics, you know that you can correlate position and momentum. Right? You can say at a certain position, your speed is this. Right? So that's why we say, okay, that's why we express the momentum in a function of position. Right? So now you say, okay, I have half of the chance of being at this position, and I know that at this position my speed is 10 meters per second. Then you can say, okay, then do this, and then plus other possibilities, right? Then this is statistically, it looks like fine for from a statistic point of view, right? Okay, any objections? Think a little bit harder. Is there any fundamental flaw when I write this down? So one thing that doesn't look that right here, I guess this is probably the reason why you ask this question is, how can you write down this? Right? This is straight out from classical mechanics. We say there's a one-to-one correlation. This is obviously wrong in quantum mechanics because there's the uncertainty principle. Right? We know that for the delta function, we already see that from a delta function. If you know that your particle is at position x1, then you don't know its momentum at all. Right? So you can't write down this doesn't exist in quantum mechanics. When you know its position, you actually don't know its momentum. Right? Okay, you actually don't know its momentum. So you can never write down the momentum as a function of position. It's fundamentally impossible in quantum mechanics. Okay, and you can actually also derive this in terms of wave. And okay, if everything described is by wave, then can you write down this in terms of x? You actually can't. You can actually try that. That's why in this momentum space, the wave function is k, not x. Okay. So this is not working. Okay, this is not working. So we tried in a classical way. So this is actually I would say like, it's a reasonable approach because if you think about it, when you try to establish a new theory, you always try to make minimum change to the existing theory, right? You don't want to start everything brand new. So you always try to make a little bit patched here, a little bit patched there. So if anyone proposed this in the 1920s, I think it's perfectly reasonable. But then like quickly you should figure out, okay, there's a fundamental confliction here, okay? Now, just like again, we emphasize this again and again, okay? We cannot know this answer of how to measure other physics variables unless we bring new experimental observations. So the physics, the chemistry, fundamentally is just using mathematics and using a field postulate to describe the phenomenon. So when you feel that you don't have enough experimental observation, okay, you cannot get the next postulate, then you should do more experiment. Now let's look at this experiment here. And this is again just the experiment of the hydrogen atom. Okay, we look at hydrogen atom experiment again. A little bit hydrogen atom, and then you charge them, and then they emit light, and then you look at the spectrum, and then here you get, this one we already know that you get, this discrete wavelength, which is proportional to the difference between 1 over an integer, right? And then also from Schrodinger equation, we already know from Schrodinger equation, let me erase this since it's wrong. Okay, this is the experiment. And from Schrodinger equation, right down here, so I use the Hamiltonian H tilde here. This one is the, meaning that this is an operator. Okay, 1 second. Okay, I remember to hit recording. Okay, so we know that I think last week we solved this briefly, right? We won't repeat that again, but let me just point out the obvious thing is that the solution is there's a position components, and then there's a time components. Right? This is separation of variables. And then when you do this, you see that the solution energy En here is simply, if you bring this back to here, okay, then your integration, your differential will act on here and then cancel this. So you will get En, okay, per psi n equals to H per psi n. Right, so it's a simple separation of variables. Okay, and then from the experiment, what you see is that the wavelength or the frequency of your light, okay, is actually equal to the energy difference, right? The energy of the photon equals to the energy difference between two electron state, right? So we can write it down as here. I can say n equals to 1. There's a hypothetical orbit. It's also called a cloud, right? Electron cloud, and 2. But it's difficult to, to plot a cloud. This is n equals 3, and keep going, right? So this is what you can solve from Schrodinger equation, and then it match the experiment in some way, right? If you assume that the energy of a photon is h bar omega. And also this is called the, if you guys are familiar with this, if you have an operation on the wave function, on a function, and what it gives back is a constant times a function, and this function is called eigenfunction. Right? This is called eigenfunction, this is called eigenvalue. And if you use linear algebra, and this is called eigenvector, okay, this is again called eigenvalue. Okay. Now so based on this, we can describe the system. Let's try it. We describe the system as the electron can be in one of this eigenstate, right? One of this orbit. And then when you emit a photon, then what you do is that your electron move from one state to another, right? One state to another, and then its energy have to change. And when its energy is changed, then the photon, emitted photon, equals to the energy difference, right? Okay, so when, for example, when you jump from n equals to 3 to n equals to 2, then you have to emit a photon that equals to n E3 minus 2, right? Energy conservation. Okay. So this looks like a nice description of your experimental observation, together with Schrodinger equation. Now let's do a thought experiment. If you look at the postulate, right, 1, 2, 3, let's try to apply the postulate into this experiment. And let's say very simply, okay, the initial state, postulate 3 said that it actually could be in superposition between two different states, right? So how about this? We say the initial state is a superposition of the third state plus the second state, right? Superposition between these two states. Postulate 3 said you can do that, right? So let's do it, okay? And then the final state, because you always have to lose energy, right? So let's say, make things very simple, the final state is the ground state. Okay? So you start from a superposition state and then you end up in the ground state. And this process, you lose some energy and then you have to emit photon, right, to satisfy energy conservation. Now the question is, what is the frequency of that photon? What is the frequency of the photon? You're not in state 3, you're not in state 2, you're in a superposition of both 2 and 3. And now you emit a photon. So what is the photon of that frequency? What is the frequency of that photon? Now I will give you guys 3 options and then you can think about it and then tell me which one you like. Okay? Let's say this is frequency, omega. And there are 2 signature frequencies, right? One is at E2 minus E1 h bar, right? It's like the state is in this second state, right? And then if jump from second state to the ground state, okay, then you emit a photon of E2 minus E1 divided by h bar. And then you also have another state is E3 minus E1 divided by h bar. Right? That also makes sense, right? If you are at state 3 and then you jump to the ground state, this is the photon frequency you will emit. Now, what if now we're in a superposition now? Okay, so what would the photon be? What would the frequency of the photon be? I give you guys 4 options and then you can kind of think about it when I describe it. The first is that, okay, it looks like the coefficient in front of the wave function are the same. So it seems that the electron is in 50% third level, 50% second level, right? So if you really think about it, okay, if you think about in terms of energy, then the average energy of this state is just the average energy of these 2 states, right? Because you have 50% here, 50% here. So because you want to conserve energy conservation, right? You want to conserve energy conservation, then the photon has to stay here in the middle. 50% from left, 50% from right, and this way you satisfy energy conservation. This is option A. Now, option B. You think that, okay, it's a little bit weird that you just kind of think, okay, maybe staying in the center is one frequency, doesn't look that well. You want to say, okay, what about, let's give it, you say there's a probability, right? Let's give it a probability. And let's say, okay, it's just be random. Let's say there's a Gaussian distribution of your frequency. It could be anywhere, but then it satisfies the Gaussian distribution. which looks quite similar to postulate 2, okay? And intuitively, it looks quite good. And then the range is from E2 minus E1 to E3 minus E2, right? There's a maximum energy of your state is this, minimum energy is this, right? So you stay in between. You never cross, these two boundaries, okay? And this is your second guess. And then the third guess is that, it's kind of the same thing, but then you say, okay, I didn't see a Gaussian here. There's no Gaussian. They're just two coefficient. So if you want to guess the probability, maybe instead of a Gaussian, it's a flat distribution. Right? It's a flat distribution. That's also a reasonable guess. The fourth guess is that how about the photon, okay, just appear at this frequency at 50% chance, and that frequency at 50% chance. Right? It's also probability. Okay. The only thing is that you're almost certain that you're violating energy conservation, right? Because you're never in the middle. Right? If you land here, then it means you actually lose some energy. If you start here, you gain some energy, right? So you never really satisfy energy conservation. So it's a little bit troublesome. But again, it looks like agree with postulate 2 and 3. Now let's do this in a zoom way, right? Okay. Anyone agree with A? You can use raise your hand function. A is showing up in the middle, always satisfying energy conservation. Okay, I don't see any hand. What about B? Gaussian distribution. Okay, I see one hand. Very good. Two hand. Good. Yeah. We always have a mystery confidence in Gaussian distribution. It's like whatever I don't know it is. We see three hand. Very good. Whatever we don't know, measure it should be Gaussian, right? As long as the number is large enough, it should be Gaussian. Okay. What about C? Flat distribution. White noise. Right? It's white. Anyone like that idea? Like a random number? Okay, you guys don't like random number. What about 4? Option D, 50-50, and then violating energy conservation. It's anyone raising hand? It takes guts to say that energy conservation is violated, right? Oh, I see one hand. Good. Oh, 2. Okay. Anyone else? Okay, so let me review the answer. The answer is D. Okay, your energy.
Isn't it because we can only have discrete energy levels?
Yes. Because you're solving this is a wave function, right? A differential equation, and then you have boundary condition, right? So your energy level is always discrete, just like the string on your guitar, right? So yes, you always have for atom you always have discrete energy level. So the answer is D. Okay, sadly it's D, meaning that it only appears either here or here. Nothing in between. Okay, nothing in between. And then you're violating energy conservation. But then overall you're not, because if you measure it enough time, you can measure it enough times, then you see 50% here, 50% here, and then you take overall energy, it's actually sitting back in the middle, right? So this is back to the Avenger movie, right? So the energy conservation can be partially violated due to uncertainty principle. Okay, so D. Okay, how can we? This is really counterintuitive, right? How can we really describe it in a mathematical way? Okay, let me try to describe it. It looks like when you do the measurement, right? When you do the measurement, the initial state behaves like it has 50% chance of in this state, and then 50% chance in the second state, right? And never in between. Okay, never in between. So never in between. And you might wonder, okay, how does that make sense? Right? Because when we say we measure something, you see that your voltage is always continuous, your velocity is always continuous, your position is always continuous. But somehow here, it looks like although you're in a state, and then it's probability, which means you can be anywhere in between, but then when you really do the measurement, it doesn't happen that way. Okay, and let me give you guys an example and then see if you guys find it acceptable. So the claim here is that the measurement in quantum mechanics looks like fundamentally different from really the statistics, right? So here's a claim, okay? People try to oversimplify quantum mechanics a lot of times, and the oversimplified version is that quantum means wave equation plus probability, classical probability. Right? It's like we know wave equation of the light, and then instead of treating the amplitude square as the light intensity, you treat it as a probability. Okay. Some people will think, okay, this means quantum. Actually, no. This is not complete, right? From this experiment, you see that the result is very counterintuitive. It means that there's something fundamentally different from when you have measurement. And in fact, you can do this measurement many times. Then what you will see is that no matter what method you use to measure energy, okay, energy. If you want to measure energy, you can either do it by measuring the energy difference, or anything. Then what you will see is that you can only get eigenenergy. Can you guys hear the noise from my mic? Or is that fine? Okay. Yeah, someone doing the mooring. Okay. Right. Just look like this. Okay. When you measure the wavelength of the light, it looks like your electron is always starting from an eigenstate and jumping to another eigenstate. Right. So you can try to do this experiment in many different ways, and they always give you the same result. Is that when you try to measure the energy, when you try to measure something, that thing only is the eigenstate or eigenvalue. You only get the eigenvalue of that quantity, right? Of that variable. If it's energy, then it's corresponding to Hamiltonian. This is operator, and then you only get the eigenvalue. Now, let's think about how we can justify that. Let's try to make it intuitive. Okay. You guys still remember, like a few years ago when you applied to college? Actually, applying to college and then the college decision process is fundamentally the same as quantum mechanics measurement. And the thought is that let's do this, and then we'll show you the similarities here. Okay, let's say you're a big fan of Virginia, and then you only apply to in-state university, right? Let's not discuss other university. And then you are lucky enough, you get the offer from the best 3 college in this state: UVA, Virginia Tech, and William Mary. And I want to left out George Mason. Okay, George Mason can come back when its ranking is a little bit higher. Okay, so yeah. Oh, I shouldn't say that. It's on tape. Okay. Anyway, hopefully, well, anyway. So and you receive these 3 offers, and then let's say you want to make a decision, right? You guys are already here, so I'm guessing that you're leaning towards UVA. Let's say 60%. And you're in engineering school. Virginia Tech has really great engineering program, so 30%. And then William Mary, I don't know much about it, so let's give it 10% out of respect. And you think, okay, that's simple. No, because your parents are paying your tuition, right? So you have a weight here. This is you, okay? Your word only counts for 50%, right? Because you're not paying your tuition. So your parents, pays your tuition, and then for simplicity, let's say your mom agree with your dad and your dad agree with your mom, which is in some cases doesn't happen, right? And then your parents pays your tuition, again 50% weight. Then let's say your parents is not that into engineering, so that the Virginia Tech rating is a little bit low. And then some parents might like the small size of William Mary, and then let's say 40% here. And then, while UVA is, always have a good name in Virginia, so 40% here. So in total, overall, you can see that the reason I choose this number is because when you add this weight together, you have 50% here, 25% here, and then 25% here. Okay, so I'm not disrespecting any other universities, but I'm just saying UVA is slightly better. Okay, so now, actually, I don't know about undergrad application process, but for grad school, there's a deadline, right? That's April 15th. Maybe undergrad has a similar deadline. Let's say before that deadline, you actually didn't make up your mind, right? So you are actually in a superposition between UVA, Virginia Tech, and William Mary, right? You're in a superposition of these 3 states. However, when the deadline approaches, you have to sign the acceptance, then you can only go to 1, right? You can only go to 1. For you guys, the measurement result of you guys are UVA, and then now you're 100% UVA. You're not 25% Virginia Tech, 25% William Mary, no matter how much you think you liked Virginia Tech or William Mary. After the measurement, you're 100% UVA. And also, there's no result saying that after the measurement, you're 50% UVA, 25% Virginia Tech, or saying that, okay, I land somewhere in between the average value. There's no such thing, right? Unless you're in a real situation, for example, Harvard, MIT, they have a joint program, right? Then you can claim, okay, I'm half Harvard, half MIT. But let's just say in this situation, there's no joint program here. So there's no way you can claim to be half UVA, half Virginia Tech, and so you land up here. So if an alien watching us from outside, and then they know nothing about our college systems, then mathematically, how would they describe it? They would describe that every year there are millions of students, okay, in a superposition state, not knowing where they want to go. Okay, not knowing where they want to go. And then there's a certain deadline. At that deadline, somehow magically, all of them did a measurement, okay, on where to go. And then the measurement result can only be certain eigenvalue. Can only be certain eigenvalue, and those eigenvalues are the college in the US, okay, maybe a couple hundred, and that's it, right? So when you measure the migration from 18 years old, okay, in the summer, it's from all of the country and then to some college town, right? Always that direction. Like when you do college, you will not stay between, oh gosh, I didn't know where is Virginia Tech. Okay, you wouldn't be anywhere in between Charlottesville and whatever town Virginia Tech is in, right? You're not in the middle. You're also not on average. You're either in UVA or you're in Virginia Tech, right? So those are you can think about the college, they are the eigenstate, they are the eigenvalues. And then when you do that, when you do make that decision, you end up there. So fundamentally, actually, in real world, many things are actually discrete. They're not continuous. Right? Many experiences you guys made, many decisions you guys made are either 1 or 2 or 3. There's limited option. There's never an average option. Right? If there's an average option, it would be great. Right? It's like you can have a little bit of both of the world, but no. Right? So this is kind of the measurement claim, that the measurement result of quantum mechanics looks counterintuitive, but actually makes sense in a lot of ways, right? If you think about it, the particles, they are discrete, right? You can count electron, there's 1, there's 2, there's 3, there's never 1.5 electron, right? If you count particles in this way, why can't you count energy in this way? When you measure the energy, there's only level 1, level 2, level 3, level 4. There's never level 1.5, right? Okay, so I want to summarize this in a mathematical way, okay, and so that we can discuss this in more details next week. Oh, well, it's only Tuesday. Okay, on Thursday. So the postulate 4, what it says is that because what we want to measure is eigenstate or eigenvalue, right? The measurement result is only eigenvalue. So the way to create an eigenvalue is that you need to have an operator. You need to have a differential equation to have an eigenvalue, right? So for any physics attribute or physics variables, for example, momentum, angular momentum energy, okay, it's corresponding to an operator, and this operator can act on your wave function. Okay, there's a operator, and then operator is kind of you can think about operator, it just means do something to this wave function, right? It could be rotation, it could be differential, it could be integration, anything that changes this wave function is an operator, right? So we already know that the x operator is just x, and then the momentum operator is h bar I partial x, and then for example, if you want to create angular momentum operator, you know angular momentum is position cross the momentum, right? So that you can actually derive that. So you need to first have an operator, and then you can get your eigenvalue. Okay. Postulate 5 is that the measurement result of a physics variable A, can only be the eigenvalue of the operator A, right? So the eigenvalue will be expressed as this: A act on function n, give you a number, a function n, right? So this is a definition of eigenstate and eigenvalue. Later, next class, we'll explain a geometric meaning of what it means really for it to be called eigenstate. Okay, so this is how you determine the eigenvalue, and then it says that the measurement result can only be one of the eigenvalues. There's no other values you can get from a measurement. And postulate 6 is that, okay, now if your state is in a superposition, right, of n different state, and each state is an eigenstate of A, right? You're in a superposition of all these states. Now, if you want to measure A, the only result you can get is still the eigenvalues. But what is the probability of getting that values? Okay, the probability of getting that value, the probability of measuring an, the nth eigenvalue, is just this coefficient in the front and then amplitude square. Okay, that's your probability of getting it. Okay, so these are the three postulates, and then we will talk a little bit more in detail in the next class. And then this is everything we have to talk about today. And there's no office hour tomorrow, so if you have any questions regarding the homework, please ask now. Okay, I'll stay here for a few more minutes. Okay, see you guys.